If I took every ocean, every cloud, every glacier, and drained them off this planet, would Earth become a dry rock, or would it still be a water world, just with its water hidden where our senses can't follow? Because if water can hide inside stone, then Earth isn't just land and sea. It's a vault. And the key is physics. Picture this with me. It's a January morning so cold the air feels brittle. You step outside and the first breath stings, clean, metallic, sharp. The world is quiet in that way winter demands. Inside, you wrap your hands around a glass of water. It's ordinary, transparent, unmysterious. A small, domesticated piece of the ocean sitting on your kitchen counter. But the longer you look at it, the less it behaves like a simple thing. Water is the chemistry of life, yes, but it's also the regulator of climate, the sculptor of mountains, the lubricant that lets tectonic plates move without locking up like rusted gears. It is, in a very literal sense, one of the reasons Earth has a personality instead of just a surface. Now here's the unsettling thought. What if most of Earth's water was never meant to be on the surface in the first place? What if the oceans we sail are only the visible fraction, like sweat on the skin of a body that is mostly water inside? Today we're auditing a claim that shows up in textbooks, documentaries, and casual conversations among geoscientists. There are oceans in the mantle. Not one. Potentially many. Hidden. And if you're like me, if you have a scientist's allergy to slogans, you're going to ask the only question that matters. How can a solid planet store ocean-scale water underground, and how do we know without drilling there? So we're going to do this like an investigation. No mystical language. No comfortable myths. Mechanisms, evidence, uncertainty, and what would falsify the idea. You and I are walking into the audit together. We're going to stand in the places where the clues arrive, on screens in seismology labs, inside machines that squeeze rocks like cosmic vice grips, and under microscopes where diamonds confess what the deep Earth has been hiding. And before we go down, we need one crucial reframe, because the entire mystery depends on it. When most people hear water inside Earth, they picture caves, reservoirs, underground lakes, a hidden ocean sloshing in the dark. That image is powerful, so powerful it can sabotage your understanding. The water we're talking about is usually not liquid. It's not a lake. It's not even H2O in the familiar sense. Deep inside Earth, water often means hydrogen, tiny, restless hydrogen atoms, and hydroxyl, OH, threaded into the structure of minerals. Imagine a crystal lattice like a grand hotel made of atoms, with repeating rooms and hallways. Most rooms are filled exactly as designed. But under the extreme pressures of the mantle, some rooms accept a guess they were never built for: hydrogen. It sneaks in as an impurity, a defect, a subtle alteration. So the planet can store water, the way paper stores ink, not as puddles, but as information distributed through structure. Water becomes hidden ink in crystal paper. That's our first emotional turn. The Earth beneath you isn't just rock. It's rock with memory. Rock with chemistry folded into it like a secret. Now, if that's true, then the next question hits immediately. Where, exactly, could Earth hide that much hydrogen? Because the mantle is enormous. It's most of the planet by volume. But it's also, on human timescales, solid. If I could cut a staircase down into it, it would feel like stone. And yet, over geologic time, the mantle flows. Not like a river, more like taffy left in the cold. Stiff. Reluctant. But not frozen forever. Convection turns the mantle into a slow engine. It carries heat upward. It drags continents around. It recycles seafloor. If you want a metaphor, the mantle is not a statue. It's a glacier made of rock. Not because it's cold, because time is so long that even solid things can move. Now let's step into the first room where this mystery becomes visible. We're in a seismology lab. It's dim. Not dramatic, practical. Screens glow in the half-light. And on those screens, the Earth is speaking in pulses. An earthquake happens, maybe off the coast of Japan, maybe along the Andes. A rupture snaps miles of rock. The planet rings like a bell. Those vibrations move through the Earth as seismic waves, some compressing and expanding like sound through air, others shearing side to side like a shaken rope. Here's the key. Seismic waves travel at speeds that depend on the material they pass through. Density matters. Temperature matters. Composition matters. And this is crucial, water and minerals can matter too, because it changes elasticity, like adding a drop of oil to a stiff hinge. You watch the arrival times. A wave hits a station, then another, then another. The software reconstructs a map of the interior, not a photograph, more like a medical scan. And in this scan, two depths keep showing up like sharp chapters in the Earth's book, around 410 kilometers, and around 660 kilometers. These are not arbitrary. They're phase transitions, places where the same chemical ingredients rearrange into different crystal structures under pressure. Let's make that intuitive. Think of carbon. Same element, different structure, and you get charcoal versus diamond. Same atoms, different architecture. In the mantle, magnesium silicate minerals do their own version of this, changing their internal scaffolding when pressure crosses certain thresholds. The region between those two boundaries, roughly 410 to 660 kilometers down, is called the mantle transition zone. And it's where the story gets strange. Because in this zone, there are minerals with names that sound like passwords: wadsleyite and ringwoodite. These minerals can host a lot of hydrogen in their crystal lattices. Not a sprinkle. Potentially a vast capacity. Under the right conditions, they can store water equivalent amounts that start to compete with surface oceans. Now pause. Feel the enormity of that. We're sitting here, holding a glass of water, and deep beneath our feet, hundreds of kilometers down, there may be a layer of rock that can hide oceans' worth of hydrogen, locked into the fabric of minerals. But capacity is not the same as reality. A warehouse can store 1,000 crates. That doesn't mean it's full. So we need evidence. And not just one kind. Because seismology can whisper clues, but it rarely gives a single, unambiguous answer. Changes in wave speed might mean water, or temperature, or partial melt, or composition. The Earth is a master of disguises. That means the audit demands something stronger, converging lines of evidence. Independent measurements that point to the same conclusion the way multiple witnesses describe the same event from different angles. So we leave the seismology lab and step into the second room. A high-pressure apparatus. It looks like industrial sculpture: steel, cables, shielding. The kind of machine you don't casually touch. In one version, a multi-anvil press squeezes a tiny sample from multiple directions. In another, a diamond anvil cell uses literal diamonds to crush material into pressures found deep inside planets. You place a sliver of mineral inside. It might be synthesized, or it might be a natural sample. Then you turn the screws, figuratively and sometimes literally, and pressure climbs until the sample is living at transition zone conditions. Hundreds of thousands of atmospheres. Here's the moment I want you to feel. We are not guessing what happens down there. We are recreating it in miniature. Not perfectly, not completely, but enough to test physics. Under these pressures, the mineral's structure shifts. Sites in the lattice open or close. Hydrogen becomes more or less welcome. Researchers measure how much water, again, water meaning hydrogen as OH defects, the mineral can incorporate. They measure how elasticity changes. How seismic wave speeds would shift. How electrical properties change. And that last one matters. Because water, even in small amounts, can dramatically increase electrical conductivity in mantle minerals. It's like adding salt to ice. You don't need a lot to change behavior. So now we have a second thread of evidence. Mineral physics says, these transition zone minerals can, in principle, carry significant hydrogen. And when they do, their properties shift in ways that should leave fingerprints detectable at the surface. But in principle, still isn't enough. Because a lab sample is not a planet. So we go to the third room, the strangest one, the one that feels almost like a seance with deep time. A diamond lab. Bright lights. A microscope. A tray with stones that look unremarkable until you remember where they've been. Diamonds form deep in the earth. Some come from depths of the upper mantle. A rarer class, so-called super deep diamonds, carry inclusions from the transition zone and even lower. An inclusion is a tiny trapped mineral, sealed inside the diamond as it grows. A time capsule. A message in a bottle thrown upward from hundreds of kilometers down. You focus the microscope. The inclusion glints, minuscule, stubborn, real. Then you analyze it, its crystal structure, its chemistry, isotopic ratios. You ask what mineral it is, and at what pressure it must have formed. This is where ringwoodite enters the story like a witness stepping into the light. Ringwoodite is stable at transition zone pressures. Finding it as an inclusion tells you the diamond formed at those depths. And in some cases, ringwoodite inclusions show evidence of significant water, hydrogen embedded in the mineral. Not a theory. Not a simulation. A physical sample that once lived in the transition zone. Now, if you're feeling the temptation to declare the case closed, hold that impulse. Because science is not a courtroom drama. It's an asymptotic approach to truth. You don't slam a gavel. You tighten constraints. So we ask the audit questions. What exactly is the claim? There are oceans in the mantle. That phrase implies abundance, continuity, something like a reservoir. But the mechanism we've described is distributed storage, hydrogen tucked into crystal lattices. What would count as strong evidence? We want convergence, mineral physics showing capacity and property changes, seismology detecting consistent anomalies at relevant depths, electrical conductivity measurements aligning with hydration, geochemistry showing signatures of deep water cycling, and direct samples, like diamond inclusions, demonstrating the right minerals, with water, at the right depths. And what would falsify or weaken the claim? If measured conductivities and seismic velocities can be fully explained by temperature or composition without invoking hydration. If inclusions systematically show dry transition zone minerals. If subduction inputs and volcanic outputs can't balance a deep reservoir over time. If models require unrealistic assumptions. Now let's thread the story together. How would water even get down there? Enter the deep water cycle. On the surface, water is mobile. It evaporates, rains, freezes, melts. But the planet also cycles water through rock over millions of years. Oceanic plates form at mid-ocean ridges, interact with seawater, and become hydrated, water chemically bound in minerals like serpentine and others. Then those plates subduct. They sink. They carry water downward like freight on a conveyor belt. As pressure and temperature rise, some hydrated minerals break down and release water, triggering melting and volcanism. That's one pathway back to the surface, volcanoes as exhalations of deep chemistry. But not all water returns quickly. Some may ride deeper, captured by minerals stable at higher pressure, especially in the transition zone. So imagine it, a subducting slab descending like a cold blade into the mantle, bringing hydrated minerals. As it warms and transforms, it releases water in pulses. Some water contributes to arc volcanism. Some is trapped. Some migrates. Some changes mineral phases and maybe accumulates in that 410, 660 kilometer layer, like a sponge between two valves. That word valve matters. Because the boundaries at 410 and 660 kilometers, the phase transitions, can act like gatekeepers. Depending on temperature and composition, they can either allow material, including water-bearing phases, to pass through smoothly, or they can hinder flow and create a kind of traffic jam. So the transition zone could be a storage layer not because someone designed it that way, but because the physics of phase transitions makes it easier for hydrogen to stay there. Now you might ask, if there's so much water down there, why isn't the mantle wet? Why doesn't it behave like sludge? Why don't we see rivers of water erupting from cracks? Because under those pressures and temperatures, water doesn't behave like a free fluid unless conditions permit melting. Most of the time, hydrogen is chemically bound in minerals. It's trapped like breath held in a chest, not spilled like a cup. Only when rocks melt does water become a separate phase and drastically change behavior. And even then, it tends to join magma, lowering melting points and changing viscosity, making the mantle more willing to move, more willing to create volcanoes, more willing to participate in tectonics. Here's where the story turns from fascinating to existential. Plate tectonics, the slow recycling of Earth's surface, is one of the best candidates we have for why Earth stays habitable over billions of years. It helps regulate carbon dioxide through weathering and burial, stabilizing climate like a thermostat with a long delay. And water is deeply entangled in that. Water lowers the melting point of rocks. It weakens minerals. It changes viscosity. It makes subduction possible in the way oil makes an engine possible. Without enough water, plates may become too buoyant or too strong to sink. So if Earth can store large amounts of hydrogen inside, then the surface ocean might not just be a backdrop for life. It might be part of a coupled system, a planet-scale exchange between visible water and hidden water that keeps tectonics, and therefore long-term habitability, alive. That's the emotional stake. This isn't trivia about the mantle. This is about why the ground under your feet is dynamic instead of dead. Now let's stress test the most seductive part of the claim. How many oceans? Sometimes you'll hear a number. 1 ocean. Several oceans. Maybe even 3 oceans. But those numbers often refer to capacity, how much water the transition zone could hold if the minerals were saturated with hydrogen. That's like saying, this stadium holds 50,000 people. It doesn't tell you how many are actually in the seats tonight. So what do we know about the fill level? We know it's not zero. Diamond inclusions and other geochemical constraints tell us water is present at depth. We know subduction carries water down. We know some returns via volcanism. But the exact inventory, how much is stored, how it's distributed, whether the transition zone is uniformly hydrated or patchy, is still uncertain. Some regions may be wetter, especially near subduction zones. Others may be comparatively dry. And that's not a weakness of science. That's honesty. The deep Earth is not easy to sample. We infer. We triangulate. We revise. So why does the ocean metaphor persist? Because it's a bridge for the imagination. It communicates scale. Ocean-scale storage is the mind's way of acknowledging that the hydrogen budget could be enormous. But it's also misleading if you take it literally. There probably is not a continuous liquid ocean down there. The more accurate picture is distributed storage, hydrogen threaded through vast volumes of rock, concentrated in certain mineral phases, possibly accumulating in the transition zone like water in a sponge, not like water in a bathtub. And this is our turning point, the moment of discovery that changes what we were even looking for. We weren't hunting for underground seas. We were hunting for a new definition of ocean. Not a place you could swim. A budget. A reservoir in the accounting sense. A planetary ledger where hydrogen is recorded in crystal structures, entry by entry, defect by defect. Now, once you accept that definition, a set of mysteries comes into focus, questions that aren't settled, but become sharper. First, the ambiguity problem. Seismic signals can be explained by multiple causes. How do we know when hydration is the best explanation? We cross-check. We look for regions where conductivity is high and seismic velocities are low in patterns consistent with water. We compare to lab-measured effects of hydrogen in wadsleyite and ringwoodite. We look for correlations with subducting slabs that could deliver water. Second, the gatekeeper boundaries. Do the 410 and 660 kilometer transitions trap water in the transition zone? Or do they allow it to pass into the lower mantle? Some evidence suggests the lower mantle may be drier, because its dominant minerals might not hold as much hydrogen. But there are still possible pathways, and the details depend on temperature, composition, and dynamics. Third, deep focus earthquakes. Earthquakes normally require brittle failure, and brittle failure shouldn't happen under the high pressures where rocks flow. Yet deep earthquakes happen, down to 600, 700 kilometers. One proposed mechanism involves dehydration and embrittlement. Water release from minerals triggers instability and fracture even at depth. If so, water is not just stored, it's active. It can influence when and how the planet breaks. And that should change the way you feel about the word solid. Because solid is a human-scale description. The Earth is solid the way a cathedral is silent, until you listen with the right instrument. Now let's widen the lens. If Earth has a deep internal water inventory, what does that do to our origin story? It suggests the surface ocean might be only one expression of a deeper inheritance. Maybe water arrived from impacts and was partitioned between surface and interior. Maybe Earth formed with more hydrogen than we assume. Maybe the mantle has been a long-term reservoir, slowly exchanging with the surface over billions of years. That means Earth's ocean could be less like a single gift and more like a visible interface of a larger system, like the part of an iceberg you can see above water, except the iceberg is rock and the hidden part is hydrogen locked into minerals. And once you see that, exoplanets look different. We look at distant worlds and ask, is there liquid water on the surface? Is there an atmosphere? Is it in the habitable zone? But a planet can look dry and still hold vast internal water as hydrogen and minerals. And a planet can look ocean-covered yet have an interior that doesn't cycle water, doesn't sustain tectonics, doesn't regulate climate. Habitability is not only about what's on the skin. It's about what's inside the bones. So the idea of hidden water becomes more than a geological curiosity. It becomes a caution. Appearances can mislead, even on a planetary scale. And that returns us to the deepest philosophical takeaway of this audit. Reality is often defined not by what's obvious, but by what's stored, constrained, and transformed. The most important parts of a system can be invisible to direct senses. Not because they're mystical, because they're encoded differently. In the mantle, water is encoded as defects in crystals. In your body, energy is encoded in chemical bonds. In the universe, information can be encoded on horizons we can't cross. The world hides its power in forms that don't announce themselves. Now let's come back up slowly. We started with a winter morning and a glass of water. Hold that glass again in your mind. Look at it like you've never seen it. Because now it's not just a drink. It's a symbol of an accounting system that spans the planet. Some of Earth's hydrogen is sloshing in oceans. Some is drifting in clouds. Some is frozen in ice. And some, perhaps an ocean's worth, perhaps more, is written into crystal ledgers hundreds of kilometers down, where pressure turns chemistry into a vault. So are there oceans inside the Earth? Here's the audited answer. There may be ocean-scale amounts of water-equivalent hydrogen stored in the mantle, especially in the transition zone, but it's not an underground sea. It's water as structure, water as potential, water as a distributed reservoir. The phrase is true in scale, and misleading in imagery. And that's the kind of truth science often gives us, not a simple yes or no, but a better mental model, one that predicts, explains, and survives stress. Now for the thought experiment I want you to carry into your day. Imagine you could press a button and instantly remove every visible drop of surface water, oceans, lakes, clouds, ice. The planet turns gray and harsh. Would Earth still be Earth? Would tectonics continue? Would volcanoes still breathe? Would the climate remain stable over geologic time? Or would we discover that the ocean we see is only the planet's shallow exhale, and the deeper breath is hidden in minerals below? That question doesn't just belong to geology. It belongs to how you think about everything you can't see, about the hidden reservoirs in your own life, stored effort, stored pain, stored love, stored memory. The structures that hold you together. And it opens the next door. If water can be hidden in rock as crystal defects, what other obvious substances might be hiding in unfamiliar forms inside planets, carbon, oxygen, even the ingredients for atmospheres? Now, if you want to keep traveling with me in this audit mindset, I have a specific request. When this ends, click the video on the end screen, because it continues this way of seeing, not just what's visible, but what's physically possible. And if you want more investigations like this, where we stress test big claims and rebuild them into real understanding, subscribe. That way you won't miss the next audit when it drops. One question for you, simple, and I'll be reading the replies when you hear oceans inside Earth. What image pops into your mind first, an underground sea, or water threaded through crystal like hidden ink?